What is up with you boys? We are live, guys. We are live. We are live. We are live. We are live. What is up with you boys? We are live, guys. We are okay, y'all. Let's start the stream, bro.
Thank God that the brothers on the rise now. Endless celebrations all in my house. Levitating now, I'm super duper fly now. London boy, but DC where I reside now. Put the time in while you always yelling time out. And for quit it, cause I know I'm coming with it. You were sitting, you were wishing I was handling my business. Now I got the ball like Harry Potter playing Quidditch. And my business so humongous, you would think that happens in it. Damn man, I'm all that, yeah, I'm all that. Looking for that whip, yeah, that what you call that. I'ma blow up in the summer, have him yelling fall back. And I've always been ahead like an effing ball cap. Man, I came in the game like, whoa. Got a couple chains on me cause I like gold. They told me I'm the best and I told them I know. Cause when I'm in your town, every ticket I sold. Yeah, they saying I'm the man. Facts, bro. Lot of haters, tell me where they at though. I'm the new pop, all I do is rap though. Want me on your song, throw a couple stacks, yo. Everybody wanna do the same thing. That's why we ain't on the same page. Do my own thing and I maintain. Flow like water, so I'm going mainstream. I'm going mainstream. Flow like water, so I'm going mainstream. Yeah, I'm going mainstream. Flow like water, so I'm going mainstream. I'm going mainstream. Mainstream. Flow like water, so I'm going mainstream. Yeah. I'm going mainstream. Damn.
Alright, y'all. Alright, y'all. Alright, y'all. Alright, y'all boys, man. So we're gonna be solving some I'm gonna be solving some problems with which have to do with prime numbers. So as we can see, we got the sieve of Eratosthenes right here. This is the most optimal way to find prime numbers up to a certain number n. So actually, let me gonna have no, actually we don't. We can stay void. We can stay void. And yeah. Alright, y'all. So first problem is count primes up to n. Given an integer n, count how many prime numbers are between 1 and n. Okay, so we already, so our n is gonna be 10. Actually, we're gonna get it, we're gonna get n, we're gonna get it from input, then we're gonna generate the sieve, and then we're just gonna have a counter. And we're gonna start at 1, at 1 less than equal to n, and we're gonna okay, what is this? And we're going to just count them. So if, so basically all of the ones who are false are gonna be primes. So if not primes of I, counter plus plus, and we're gonna see out primes of I as well, like this. And we're gonna see out a new line, and we're gonna see out counter Let's see how the counter with a new line as well. And let's see, for input 10 we should get 4. Okay, we get 5 though. So it's between 1 and n. 2, 3, 5, 7. Why do we get this as well though? Because it should be less than n. Okay, we still get 5 for some reason. Okay, I think we actually need to start at 2 because then how many prime numbers are between 1 and n. Okay, let's Okay, now we get 4, not primes. So yeah, basically this is the case because we also have 0 and 1. And okay, so we also gotta say and I greater than 1. So now we can start from 1. Let's comment this out. So now we can do 10 and we get 4. Okay. Oh, okay, I get where we got. We were C outing primes of I. I mean, we also see out we see out the primes here as well, and we were C outing primes of I, which is not a number, but which is false because the array is full of true and false values. So yeah, that is basically it for that one. That is basically it for that one. So how does the sieve work? So how does sieve of Eratosthenes work? So the sieve of Eratosthenes is an ancient and highly efficient algorithm used to find all prime numbers up to a given limit n. So that's why we create a Boolean array called primes, which is going to include n plus 1 numbers, okay? And initially all of them are going to be set to false. And basically we're going to set all of the multiples of the prime numbers to true so we can skip them. And we're going to use only the prime numbers. What's up, Aziz Beck? What's up, bro? What's up? Welcome. So it works. So it's okay. The sieve is an ancient and highly effective algorithm used to find all prime numbers up to a given limit n. It works by systematically sifting out composite numbers. So composite numbers are non-primes by crossing off the multiples of each prime. So we create a list to write down all the numbers from 2 up to the chosen limit n. 1 is not prime, so it's ignored. We find the first prime, we start at the first unmarked number, which is 2, and we identify it as a prime. Then we cross out, we go through the list, we cross out the multiples of 2. So we go through the list and cross out all higher multiples of that prime. For example, 4, 6, 8, 10, because they are composite. Then we move to the next unmarked number in the list, which is gonna be 3. Then we're gonna cross out all the higher multiples of 3. So 6 is already crossed out. The next one is gonna be 9. 12 is already crossed out, so the next one is gonna be 15. Then we move to the next unmarked number. So on the next iteration it's gonna be 5 and so on. So we stop. So we only need to check numbers up to the square root of n, and any composite number larger than square root of n will have already been crossed out by smaller primes, and the final result, all the numbers that remain are unmarked are prime. So right here I have pulled up a visualization. So we ignore the 1, we start at the number 2, okay, and we cross out all of the multiples of 2 up until n inclusive. So in this case n is 49. So first we're gonna cross out all the multiples of 2, okay, then we go to the next and we're gonna mark them in the array as true, as we do here. We mark them in the array as true. Then we go to the next unmarked number, which is 3. So we're going to have 3 selected, and we're going to cross out all the multiples of 3 in the array. Alright, so that's basically it. We have crossed out all the multiples of 3 now. Then the next unmarked number is 5. So we're gonna cross out all the multiples of 5 in the range, and then this goes only until square root of n, and the n is 49. So then we have the last one, which is 7. We're gonna cross out all the multiples of 7, and that is basically gonna give us all of the prime numbers in the range. Okay, and this is faster than looping through. This is the most efficient way to generate prime numbers, basically. All right. So yeah, that's basically that. So we can see how much faster is sieve of how fast so how okay, so how fast is the sieve of Eratosthenes compared to checking if each number in range is prime? Okay, so when finding all prime numbers up to a given limit n, the sieve of Eratosthenes is drastically faster than checking each number individually known as trial division. The performance difference expands rapidly as n grows larger. Okay, so that the time complexity, the mathematical efficiency of both methods reveals a significant performance gap. So if we check all the numbers individually, to check if a single number n is prime, you need to loop up to n square root of n to find factors. When doing this for every number up to n, the total time complexity is going to be O of n times square root of n. And in the sieve of Eratosthenes, instead of checking for factors, the sieve starts at the first prime and crosses out all its multiples in an array, because it uses addition rather than division and skips already eliminated numbers. Okay, so its time complexity is O of n times log of log n or something. The term log n grows so slowly that it is practically a small constant for any number manageable by a computer. For all practical purposes, the sieve runs in the near linear time. Alright, and we can see as the input grows how many operations this is gonna do or something. Yeah, so individual check operations and then sieve operations. So the difference in execution speed corresponds directly to the total number of operations required. So if we use the individual check with And when n is 10,000, we're gonna have about 1 million operations. And if we use the sieve method, we're gonna have only 25,000. So that's about 40 times faster. If n is a million, we're gonna have about 1 billion operations. With the sieve, we're gonna have only 4.3 million. And if n is 100 million, we're gonna have about 1 trillion operations, and the sieve is only about 520 million, so that's almost 2,000 times faster. So this is why the sieve is very efficient. So the sieve wins. Yeah, so basically the trade-off is the memory, because the sieve takes up extra memory, but no algorithm is perfect. Each algorithm has its pros and cons, and that's why basically why we use the sieve. Okay, I think you guys maybe got a little bored by that, but I think it's pretty cool. So, and I wanted to explain that to you guys. So next problem is print all primes up to n. So given number n, print all prime numbers from 2 to n. So basically we're gonna get rid of this. Okay, and basically this is already what the code is doing already. So we're just gonna, so we have 20, and this is gonna give us all the prime numbers to 22, 3, 5, 7, 11, 13, 17, 19. Okay, and that's basically all of them. Alright, then we got what we got, maybe something like 100, why not? So we get all the prime numbers from 2 to 100. Okay, alright, so this is basically gonna run until square root of n, and if the current number is a prime number, we're going to set j to the current number times 2. So if this was 2, it's gonna be 2 times 2, which is 4. And while j is less than or equal to n, we are going to perform this operation. We're going to increment j plus equals 2. So this is gonna start at 4. It's gonna set 4 to true, which is gonna make 4 not prime. Okay, we're just gonna mark 4 as composite. Okay, what this one here? We're just gonna mark 4 as composite. Afterward, first it's gonna mark 4, okay? Then it's going to be 4 plus equals 2, which is 6. Then it's gonna mark 6. Then it's 6 plus equals 2, so it's gonna mark 8. Then it's 8 plus equals 2, which is gonna mark 10, and so on. So if we select 2, we see that we mark 4, 6, 8, 10, and so on. And we basically do all of this marking until square root of n. Alright. Keep grinding. Thank you. Thank you, bro. I will keep grinding, bro. Thank you. Thanks for the support, man. Appreciate you. Appreciate you, man. Alright, so we did this. So we're gonna check if multiple numbers are prime. Okay, so we get 3. Okay, so prime, not prime, prime. Determine that each number is prime. Okay. Okay, so we're gonna queue queries. So we're gonna have queue, we're gonna see in queue, we're gonna do while q minus minus we're going to get n CNN. We're gonna make the vector with the primes. We're going to run sieve of the primes. Then we're going to so 3, 7, 8, 11. So we're gonna start from 4. Okay, we just need to. So we have the primes. We just need to use the index. So if primes of n, if not primes of n, because all the prime numbers have a false value, we're gonna see out prime, else we're gonna see out not prime. Okay. Happy birthday, Bert. Thank you, Beyond. Thank you, bro. Appreciate you, man. Welcome to the stream, bro. Thank you. Welcome to the stream, bro. Thank you, thank you. Okay, so we're gonna get 3, then we have 7. Okay, so we're gonna let's comment this out. I'll stop this first. So we're gonna run this. So we're at 3. So 7 is prime. 8 is not prime. And 11 is prime. So yeah, that's basically it for that one. Alright. So the next one is find the largest prime less than or equal to n. Given n, find the largest prime not greater than n. Okay. So we're just gonna remove this. Remove this. So we're still gonna generate the primes. So then we're gonna have, let's say, our answer. We're gonna go through the primes. We're gonna go to the primes less than n plus plus if not primes. So if it's a prime number, we're gonna say that answer is equal to primes, actually I. Okay. Okay, but we do have that case where it could be. So we're gonna see if ans is 0, see out no primes or something, and then else we're gonna see out ans. Okay, so we get 20. Okay, we get 19, so that's the largest prime number not greater than n. So then let's say 100 or something, and we'll get 97. Let's say we get 2 or something, and that's gonna be no primes. Alright. Okay. Okay, so that's that one. Okay. Okay, so next one is sum all primes up to n. Okay, so compute the sum of all prime numbers from 2 to n. Okay, so let's keep the answer variable to n. I'm guessing n inclusive. So basically, if it's up, we just have to check. We just have to basically just add this, and basically that's gonna be the answer. That should give us the answer. Alright, so we get 10, we get 17, and that is correct. So I already discussed how the sieve works. I showed you guys uh, the visual of how the sieve works. Then I showed you guys how much faster the sieve is, in comparison to the brute force approach. Okay, so that's what we did up till now. So let's say 50 or something. Okay, guess that's the answer. Okay, let's be something that is. Okay, let's actually see out I. Okay, I'm gonna see out a new line just to make sure. Let's say up to 5. It's gonna be 8. Oh no, it's 10. Yeah, 2 plus 3 plus 5, that's 10. Okay, let's say up to 10. 2 plus 3 plus 5 plus 7 is 17. Let's say up to 20. So this is 10, 10, 17, 17, 28, 28, 28, 40, 28, 41, 41, 58, 41, 58, and then 58, 60, 77. So 58, 10, 58, 10, 9, yeah, 77. Okay. Alright, seems to work. Okay. So, okay, so that's gonna be it for that one. Done and dusted. Let's get to the next one. Count prime numbers in a range. Given L and R, count how many primes are in LR inclusive. Pretty sure this means inclusive. Okay, so we're just gonna have, we can use ans again. This time it's gonna be ans plus plus though. Okay, so we don't need this. Okay, actually we can see out I again. Alright, then we can say, okay, we're gonna see out the answer. Okay, then we just need L and R. So we're gonna have L and R, we're gonna see in L and R, and now the amount is gonna be R plus 1. We pass in N, so that's gonna be R. Okay, and that should be it, I think. Okay, what happened? Not declared. Okay, so it's gonna be Wait. Okay. So it's less than or equal to R. This is L. Okay, so 10 and 20. Okay, it's not. Wait a sec. Okay. Okay, we'll go 4. So this is something like 1 and 20 or something. Okay, we get to 1 for some reason. And I greater than 1. So, okay, so I don't check the case where okay, we're just gonna say for simplicity and I greater than 1 for simplicity. So it's gonna be 1 and 20. Okay, so it's 8. 1, 2, 3, 4, 5, 6, 7. Haha, 8. Okay. Appreciate y'all, boys, man. Appreciate y'all, boys. Appreciate y'all, boys. Okay, that's that one. Okay, twin primes. Count pairs of primes up to n. So p and p plus 2 up to n. Okay, so basically we need 2. We have, okay, we're gonna get n. We're gonna get n from input. There we go. I'm gonna start from 2 is equal to n if primes are I. So basically, if not primes are I and not primes are I plus 2, okay, then it's gonna be okay, let's see if something, then we're gonna see out this comma I plus 2, and we're gonna increment the answer. Okay, so let's see if this, okay, so it kind of messed up, so and I plus 2 less than what is it, primes dot size or something. Okay, now we got 4. Okay, 5, 5, 7, 11, 13, 17, 19. Okay, just my printing is wrong. My printing is okay. We should probably have a new line. Okay, there we go. 3, 5, 5, 7, 11, 13, 17, 19. Okay, Goldbach pair given a even number. Find 2 primes whose sum is n. Yeah, today I also learned that if you add up 2 odd numbers, it gives an even number, which I didn't know. Given an even number, find 2 primes whose sum is n. Okay, whose sum is n. So we can check if the current is prime, and then we can subtract the current from the input, and then we can try to find the subtraction if it exists. So we're gonna have n, we're gonna have if is not primes of n minus I mm, let's say that of n minus I n minus I, so okay. Okay, let's go to the next one. Find the cave prime, generate primes with sieve and index them. So okay, let's try this. So primes of n minus I, we're going to, we can just see out I and n minus I, right? Pretty sure. Pretty sure. Into primes. Okay, so then we're gonna break. Then we're gonna break. Okay, there we go. Now let's try. What else can be? 30, is 30 possible? Okay, it is possible. So that's 30. Okay. 50, I don't know. Yeah, 240, 47. Okay. Okay, so that one works. That one works. Back pair easy version. Find the maximum difference between consecutive primes up to n. Consecutive primes up to n. Store primes and compare neighbors. Get between 7. Oh, okay, so we're gonna between consecutive primes. So basically 11 minus 7. Okay. Okay. So we're gonna have n again. We're gonna have ans. So if primes of I, if not primes of I, and not primes of I plus 1, primes of I plus 1, if I plus 1 minus I is greater than ans, that's gonna be I plus 1 minus I, or something like that. Just see out ans, or something like that. Okay, so that doesn't give. and 11. Okay, so let's just see out I plus 1, 2 and 3. 2 and 3. Okay, wait though. If not, see out. Okay, so if not primes of I. Okay, so the next number is not gonna be, so it gives me only 2 and 3 because 2 and 3 are next to each other, while 5 and 7 are not next to each other. The next prime of f next to 5 is 6 and not 7. Haha, 6, 7. So the next prime is 7, so it's gotta be, so if not primes of I, we're going to say int j is equal, we're going to have int j or something, and which is gonna be equal to I plus 1, and while primes of j, I'm going to say j plus plus, and then we're gonna say ants if we're gonna say uh, if j minus I is greater than ans, then we're gonna say ans is equal to j minus I or something. Okay, there we go for. Okay, so that's that one. So let's even see out j and I like this. Okay, so first we got 2 and 3, which is 1. Then we got 5 and 3, which is 2. Then we got 11 and 7. So first we actually want first is, and then this. Let's actually also print all of the prime numbers as well to make things even more clear. Okay, so we have these. We also need a new line. Okay, we don't need this new line. We don't need that. Okay, and 20. Okay, there we go. That's 2, 3. Okay, actually, let's do a comma, and then we're gonna do this. Okay, there we go. So we got 2, 3, which is 3 minus 2 is 1. So that's not the final answer. Then we got 5 and 3, which 5 minus 3 is 2. So that's bigger than the answer we have already. So we said that. But then we have 11 and 7, which is bigger. which 11 minus 7 is bigger than 5 minus 3. And then we get 4. Let's try a bigger one. Try a bigger one. Okay, so now we got, so 19 minus 17 is 2, 22 minus 19 is 4, 29 minus 23 is 6. Nice, so that's the biggest difference. Okay. Okay, seems to work. Okay. Okay. So next one is find the cave prime, and this is actually, so guys, this is gonna be the last problem of this is gonna be, we're gonna solve this and then we're gonna end the stream. Okay, so I mean, this is, we couldn't have ended on a more easier note. We just need to basically, given k, I'll put the cave prime number. So we just couldn't have been given an easier one. So generate prime number, receive and index them. I'll put the cave prime number. The cave prime number. Okay, let's see. We have 100. And we have all the prime numbers until, let's say our sieve is, I mean, we're gonna simplify this, you know, we're not gonna do all the edge cases. So we're gonna output the cave prime number. Okay, so let's remove this. So initially we have the 0th prime number. Okay, so if not, so we're gonna have k, if not primes of I, we're going to increment answer. If answer equal k, we're going to break. Then we're going to see out. Okay, wait, no. Mm, mm. Alright, we're gonna count that. Okay, so now it's gonna be, the cave prime number. Index them. So it's gonna be actually, so if not primes of I, I'm going to say ans plus plus. We can actually have I outside. Okay, we can have I outside, and we're going to be incrementing I. So if ans equals k break, and we're just gonna see out prime, we're gonna see out I, and this should be, that should work. That should work. Okay, stop run. Okay, so that is 2257. So plus plus, or we see an N, we're gonna see an K. So that's 6. Okay, there we go, 13. So let's say we want the 7th. Okay, that's 17. 1, 2, 3, 4, 5, 6, 7. That's the 7th. And then let's say we want the 4th or something. And that's 7. So, okay, actually, wait. 6. 1, 2, 3, 4, 5, 6. So there should actually be signature receive. Yeah, that's it. Does work. It does work. It does work. Okay. All right, y'all. So that's gonna be it for today's stream. I solved all the 10 problems. So that's gonna be it for today. Thanks to everybody who tuned in. Appreciate